Think, make, break.
Hi guys, we're at UP FabLab and we're going to learn how not to fry a diode powered by an Arduino. It's a pretty long title.
An LED is actually an analog electronic component. And then trying to put an analog electronic component into the digital circuits, and it's like, wow, and then you fry it. Right. Electrical systems or analog electronics is ruled by a lot of quite complex equations if you really want to take into account all the parameters, right? Everything is imperfect, all the components are imperfect, but it's at the beginning when you're trying to understand, you make the assumption that all the components are actually perfect. A power source which gives you, so for example, a power source that is going to give you 5 volts, right? It's going to give you 5 volts whatever you connect to it all the time. Even if you try to put try to put it straight to the ground, it will send an infinite amount of current, right? Which is obviously not true in reality, right? But when you start with electronics, you assume that your systems, all your things are perfect. When you start advancing in your circuit, then you're going to start making, oh, I'm going to remove this assumption, this is not perfect anymore, this has a resistance in it, all these kind of things, right? And you're going to see why things don't work or why they fry, in particular your LED, which is in that particular case acting as a fuse. So in digital electronics, high or 1 or whatever, usually either 3.3 volts or 5 volts, depending on what components you use. But in the Arduino, the basic Arduino, we know it's 5 volts. You have 5 volts coming from a pin. I'm going to assume it's a perfect source of 5 volts and it can actually send an infinite amount of current, which is actually not true. Put those 5 volts onto that LED and you see it lighting up for a very short amount of time. The way they work is that they leave the current goes one way, but not the other. And when the current goes in that particular direction, when they open, so they open for the current going this way and they close for the current going the other way. And you can make a good approximation to say that when the current goes through them, the voltage from between that point and that point is going to be 0.7 volts. They always try to keep that 0.7 volts there. So you understand the problem here is that between that point and that point, you need to have 0.7 volts, but that guy here is giving you 5 volts, so there's a problem in the circuit, right? 0.7 is not equal to 7 because the tension is the same. So what's happening is, to increase the voltage between that point and that point, then we're going to start understanding now that nothing is perfect, is that the diode or even the wire which is connected to the diode is not perfect, it has a small resistance. So it has a small resistance, and the symbol for resistance is that thing, right? And it's resistance R, which is very small. So basically you have another voltage here. Let's call it X for the moment. We don't know what it is. But what we know now is that 0.7 plus X equal 5 volts. So now we know that X is going to be 5 minus 0.7, 4.3 volts. So you know you have 4.3 volts there. Ohm's law says that U equal Ri, so the voltage is equal to the resistance times the intensity. And we know this is small. We know this is 4.3 volts. We know this is small. We don't know exactly how much, but it is small. And this is high. Something small, and then you don't know what is your intensity here. But then you suddenly realize that the intensity of the current that's going to go through here depends on that resistance here. So the smaller the resistance, the larger this, because this product is always equal to 4.3 volts. So in fact, I equal 4.3 divided by R, which we know is small. If that was 0, then this is infinite, which is very bad, right? But this is very small, it's going to be very high. So let's say I'm going to put an arbitrarily small number. So let's assume it's 1 ohm. So if R equal 1 ohm, it's divided by 1 and it makes 4.3 amps, which is, if you know a little bit of electricity, 4.3 amps is a fair amount of current. It's not huge, but let's think that your electric breaker, right, in your house usually is going to stop, is going to tip off at about 10 amps, 15 amps, maybe 20 amps, right? Usually you have fuse at 5 amps, right, to make sure that things don't fry. So 4.3 is not a huge amount, but it's very significant. Definitely much more than a digital circuit will give you anyway, right? Mm-hmm. Yeah, 4.3 amps going through that resistance here. The laws of electricity is telling us that this electricity goes through here, is also going through here, is also going through here, and is also going through here. So you know you also have the same amount of current going through your diode. So your diode, which is now being illuminated, receives 4.3 amps, assuming that the resistance is 1. Now if you look at the back, at the specification sheet of your diode, you're gonna see that your diode is probably rated at 20 milliamps. Some of them are like, yeah, it's rough, it could be 50, maybe it's 100 if it's a big one, right? 100 milliamps, but it's not 4.3 amps. Therefore, you are sending way too much current through that stuff. It's going to just flash and burn out and melt, pretty much. That's what's happening. That's why you're killing the diode.
So does that resistor go somewhere?
Yeah, so that's exactly what we're going to do. To reduce the amount of current, you just have to find the value of R here, because you can add R to a circuit. That's very easy. It's just adding a resistor into a circuit. That's going to make that I is equal to about 20 milliamps, and then you'll be happy. In fact, it's not that equal, you don't really care. You just want to be less than 20 milliamps, approximately, right? Because if it's more than 20, if it's rated at 20 milliamps, means it can keep 20 milliamps for a very long time without dying. If you have less, then it's okay. If you have like 10 milliamps, it's probably fine. It's just going to be not as bright. That's it.
Ideally, how much would you use?
Ideally, it depends on the spec of your diode. 20 is probably common.
Like how much resistance or how much?
Oh, we're going to calculate it. So if you want, let's say you want actually 20 milliamps, so I'll make an equal now, right? 0.02 amps, right? Is that 20 milliamps? Yeah, that's 200 milliamps. We have to send this one on the other side, so I'm going to change my equations a little bit, right? 4.3 volts equal 0.02 amps multiplied by R, and then R is equal to 4.3 volts divided by 0.02, and then I need a calculator. Can you actually do this division for me?
Isn't this cheating?
4.3 divided by 0.02. 215 ohm. That's it, right? If we put a 200 ohm resistance, you're gonna have roughly 20 milliamps there, maybe 21 milliamps or 22 milliamps or something like this, right? And then you have a diode that works, that doesn't fry. This is how you do not fry a diode, by connecting it to a digital circuit which sends 5 volts. Why you fry diodes by connecting them, and how to not fry them by putting a resistor.
Next time I will bring a tripod. My answer.
Cool.
So what are we doing right now?
We're looking at the resistance of a particular resistor. So that's 1000 ohm. Brown means 1, black means 0, and red means 1 multiplier of 1K. Usually a good way to do things, we call them breadboard in electronics. And the way they work is that the top two lines and top bottom lines, they're all connected together. So all the top there is all connected, and all the second line on top is all connected to each other, but they're not, the top and the bottom one there and the top one there are not connected to each other. They're independent. Same here, so they're connected that way. And here in the middle, nothing, that line cuts everything. Otherwise, all the vertical ones are connected to each other. Okay, so for example, I'll just explain. If I do this and that, those two wires are now connected because they are on the same vertical thing. If I go there, they are not connected. Okay, here, between there and there, they are connected. There and here, they are not connected. There and there, they're not connected. Like if I put them next to each other like this, they're not connected. That's not connected. Okay. So here it's horizontal connection, and here is vertical connection. And it just helps making building circuits very quick. So it does. Usually we use those bottom and top as what we call the power rails. So we put negative is going to be the ground, and the positive is going to be your voltage, right? Usually 5 volts. So I'm going to do this. I'm going to take the negative here, and I'm going to connect it to the ground. And there is 2 pins here with G and D, and I know the ground. So this is the negative is not connected to ground.
So this is our power supply?
Yeah, I'm using the Arduino as a power supply. And then I'm going to take the second rail, and I'm going to connect it to the positive here. And there's 1 pin which is written like here 5 volts. and that should be 5 volts.
So how many volts is the output of the Arduino?
5. It's
5.
digital.
Everything
Everything is either 0 or 5 volts. There's nothing else in between on this Arduino. That's the general rule for Arduino. So what I'm going to do here, I'm going to actually test that I actually have 5 volts coming out of this. I'm pretty sure I do. So I'm testing between those two rails, what is the voltage, and I should get something which is about 5 volts. I mean, I'll put them the reverse way around, right? So I'm reading minus 5 volts. I actually put my negative here on their positive.
You don't have to be accurate, right, to the
No, it's you know, everything, all the components that you use have like what we call a tolerance, right? And they approximately, for example, those guys here, the last ring is a gold ring. The gold ring means they are plus minus 5%. So you don't know, it's like if it's a 1000K, it could be plus 5% of that or minus 5% of that, you don't know. There's an error of 5% on them. Usually you're gonna get the signals, everything is going to be at plus minus 5% pretty much everywhere in the circuit. 4.95 or 5.05, it's fine. You're just like within your 5 volts. There's this 1K resistor, right? And we're going to jump it between the plus, right, and somewhere, let's say here. So which one we said was the positive? Was the long one? Right. So now I put the positive there because that's 5 volts. That's 5 volts. For the moment, there's no current. So since there's no current flowing through the resistor, the voltage across the resistor is 0. So that's 5 volts. And I just put there, and then I'm going to connect back to it. And then when I connect the ground, I'm going to close the circuit and it should light up. And it doesn't, so something wrong. Either because it's the other way around, which is possible, in which case I got it wrong, or maybe the thing is already fried. There you go, it was the wrong way around. And it lights up, right? And you can see it's pretty dim, right? And that's to be expected because remember, we said that we're going to use a 200 ohm resistor, but I put a 1000 ohm resistor because it didn't have a 200 ohm resistor. So I actually have 5 times less current in there than I wanted originally. So instead of having 20 milliamps that I was calculating, roughly, I put divide that by 5. This is for practice. You go there and you actually make it happen. Usually, the breadboard is very good to do a prototype circuit. You start collecting all the things you want to do and see if they work correctly. Then once you have a circuit that works exactly the way you want, then you're going to go and then make a proper print on a piece of copper, right, and install the things correctly and all this kind of stuff, right? So this is a prototyping phase. The first one is the thinking phase, calculation, how much resistance I'm going to put there so I don't fry my system or whatever, right? Then you prototype it and test it, make sure it works. And then once you have tested it and you actually want to make your product, then you go into like more of a production mode where you're going to make something which is more robust. Because something like this, then I bump it and then yours stops working because one of the wires gets disconnected or whatever. So this is only for prototyping. And then if you actually don't put a resistance there, if you actually bypass the resistance, you're going to see that LED is going to actually become really strong and then even fry quite quickly. Then it's already dimmed up now because I've fried part of it.
Oh, okay.
Ah, okay.
Right? So it's actually not happy anymore. Yeah, because you put so much current through it and it's not supposed to do that. And you're just like unhappy. And if I leave it there, it will stop working.
Right.
And then we'll control it in a bit.
Easy pizza.